Hello everyone, welcome to lecture number 5. This is the analog to digital converters. And so in this lecture, these topics will be covered. The first one is the ADC topology, the operation principles of analog to digital converter, and the input and noise cancellation techniques used in microcontrollers with reference to the ADC, and ADC characteristics, and the operation of ADC inside the AVR microcontroller. Here I'm using 8MEGA328P microcontroller, and few example codes using Atmel Stereo. Right, so analog to digital conversion is, I hope you might have some background. So only few pins of the microcontroller can be used for analog inputs. So analog signal, it's time varying signal. Like digital signals are something like ones and zeros, and analog signal is time varying. It doesn't have either. It could be VCC and 0 for digital signals, and analog signals can have different levels of voltages. Okay, with respect to the time. So not all these pins of the Atmega microcontrollers can be used as analog. So these pins are available for you to deal with the analog. Like I mentioned, in real world, most signals exist in the form of analog, time varying with different voltages. The devices such as temperature sensors, light level detectors, weight scales generate continuous, either it could be voltage or current signal, which is known as analog signal, right? So it is basically with respect to the time, the voltage or the current can be varied, right? So when you're coupling to an analog signal for processing, make sure you are not exceeding the maximum voltage, which is the VCC. Sometimes you can go up to 0.5 volt, VCC plus 0.5, and not the analog signal sometimes can go below the ground level. So you should not letting it to go below -5 volt. Otherwise, the port pin will be damaged, right? So you need to know about the characteristic of your analog signal, and then you can couple it to analog channel. If this voltage is too much, you can use resistor dividers. In most of my projects, also I'm using resistor dividers when I need to measure something like a voltage level from 12 to 0, something like changing like this. So the microcontroller is accepting voltage levels from 5 to 0. So you can simply use a resistor divider and connect it to the mesh to the level which vary from 0 to 5. Otherwise, it could harm the microcontroller. So the calculation of resistors is up to you. You can calculate them and map the voltage to the desired level of the microcontroller. So, like the analog signals cannot be processed inside the microcontroller. So you need to convert it to a digital value. So in order to do that, you need to have an analog to digital converter, which is something like a specific hardware is for that ADC inside the microcontroller, which will do the performance of ADC coming from these analog channels. Then it will you can use a digital number respected to the analog signal. So here you can see the dedicated AVR Atmega328P microcontroller pin numbers. So, and you need to provide this, there's an ADC hardware inside. It's a hardware. So it should be powered up. So you have to have a ground connection and positive voltage connection, AVCC, like this is VCC for digital, and this is VCC4 analog. So you provide the plus and minus. Then you need to have some kind of reference voltage. You could use a like external reference voltage, or it could be a band gap reference or reference IC or in a diode or whatever, like a fixed voltage. You can provide to this A reference. So if you don't have, you can use an internal voltage reference. Inside the microcontroller, there's a band gap reference. So it's like a fixed voltage source. You can use it for the ADC. Or sometimes you can use the VCC pin for the reference, right? You can, there are some options for use the reference voltage. And once the power is there, so you can pick any of these pins which is coupled to any analog signals to convert this analog signal to digital signal, right? So you can do one at a time, right? Even though there are multiple pins, so you can select one and get the number, and disable this and select the other one and get the number likewise. Like you cannot do parallel computation because you have only one ADC converter. You don't have like multiple ADC converters to run this ADC in parallel. So by using this one, either you can use one channel and do the ADC and stop it, and then to select the other channel and do the ADC. So when you have multiple signals. Right. So any analog pin, like if you select any analog pin, so inside, this is what is available to you, right? This pin, but internally it is something like that. So inside the microcontroller, there's a series resistor which could vary from 1 to 100 kilo ohm, and there's some parasitic capacitance which is 14 picofarad, which is connected to the half of the power supply voltage. So you need to charge this capacitor to some level. So like this is your signal, and so this voltage here should be equal to this value in order to do the ADC, right? But there's a capacitor and resistor RC circuit, so there's a time lag. So this is the original signal here, but what is appearing here is time lag, something like it is behind, right? Because it takes some time to charge this capacitor. So real fast signals cannot be processed because it takes some time to charge the capacitor. It depends on this resistance and this capacitance. Sometimes, so your signal, what is coming here, is coming from maybe like an external circuit, like a voltage source, right? Maybe a voltage source. That voltage source has an internal resistance, output impedance, which goes there. So it is recommended to have this impedance of your source, which generating this analog signal very low, right? If this is also high, and this resistor and this R plus this one will take time to charge this capacitor, so it will take more time, and your signal is more lagging behind the real time, right? So the use is recommended to only to use low impedance sources. So this R should be very much low. Most of the cases it could be less than 100 ohms. So it is recommended to use this resistance less than 10 kilo, right? Should be less than 10 kilo. So whatever the analog signal that you're coupling here should have output impedance less than 10 kilo ohm in order to work this ADC converter properly. Otherwise, you will find some troubles, right? And also this, there's a theory called Nyquist frequency. So like say this signal has a like 1 megahertz frequency, right? So your ADC processing speed should be at least 2 megahertz, right? So your processing speed is 2 megahertz, then only you can sample this 1 megahertz. So if your processing is 1 megahertz, this is not the internal clock or the oscillator, but ADC, it also has a different part to have a clock signal. It's a grayscale. If this is, you cannot use any frequency less than this frequency, which is called as Nyquist frequency, right? While having 1 megahertz, you cannot sample 1 megahertz signal, so you get error values. In that case, at least you need to have 2 megahertz operating frequency of your ADC, right? So if you have, this is the highest frequency component of your signal. If you have more high frequencies like 10 kilohertz, 10 megahertz or something, by using 2 megahertz, you cannot capture that kind of high frequency signal, right? Only the low frequency could be captured, but you cannot capture this high frequency due to this Nyquist criteria. And sometimes if you're having this kind of your AD analog signal should be something coming from a robot arm or any kind of sensor, it might have some kind of noise signals, right? So in that case, you need to couple this ADC signal using some kind of RC filters to remove this kind of noise and get something like a very smooth signal, removing these spikes, right? Then only you can get some accurate reading. Otherwise, it will sample this noise as well, so that will give you some error readings. So it is always not about the programming, or you need to have some kind of background about the hardware as well. When designing an embedded system or PCB layout, you need to pretty much careful what you are dealing with. It's not like a pure programmer might be write a good code, but it will not work in real world due to different characteristics that I have mentioned, like this kind of Nyquist theorem and high frequency components and this charging capacitance due to this impedance of your source. And you need to deal all these things. That's why we as engineers and technicians are different from the programmers, right? Different from the computer programmers. So you need to have both hardware and software skills in order to make a working device or working system, embedded system. All right. So there are some analog noise cancellation techniques when you're using the ADC. You cannot just directly couple any ADC to any pin and get the work done. So you have to deal with this kind of manufacturer recommended techniques in order to get your circuit working properly. So, like sometimes in the microcontroller system or embedded systems, sometimes you are using some digital pins like switching LEs or PWM to control motors. Like this kind of digital signals generate electromagnetic interference, right? That is like it could be radiated or it could be conducted emissions, which might like using magnetic field that this signal can moving in the PCB trace, and that can generate a magnetic field. That magnetic field can couple to your ADC pin and generate some kind of noise, right? So due to this fast switching of digital pins. So in that case, the noise of this nearby digital pins can affect your ADC reading. So you have to be careful. That's why these kind of recommendations are provided by the manufacturer. The first one is, do not use this VCC pin directly coupled to your AVCC, right? So I have seen many people just coupling this one here, right? So this is a digital VCC, and this is digital ground, and this is analog VCC, and there's an analog ground, right? So you have to keep them separate. If you are if you just want to use this VCC, make sure at least you're using this LC type filter, and then couple to this AVC, because this is 5 volt. You need to have a 5 volt supply here, so you can't always rely on a separate supply. So you can connect this VCC supply using a RC filter, like using a ferrite bead and a simple ceramic capacitor, so that will eliminate any noise happening in the digital signals coupling appearing in your ADC, right? So that's a very good practice when you designing prototypes, right? So it is also recommended AVCC should not be less than plus or minus 0.3 volts. So like if you're using 5 volt, make sure your tracks, this track is not having any loading effect or any resistance that will push your AVCC down 4.7 volt, or sometimes it should not go beyond 5.3 volt, right? So otherwise you will not get any useful values from your ADC. Right, for the AVCC reference, so there should be some reference voltage, otherwise the ADC will not work. You can either connect any external DC power source to here, or you can use the internal band gap reference. This is option 1. You can connect external, or you can use the internal 1.1 volt supply. Or you can directly use this AVCC supply for the reference. So in that case, you can just couple this AVCC. Sorry, you don't need to connect it externally. You can just connect the capacitor here and connect it to the ground. So then it will use the AVCC, and you have to define few values for the registers to select this value. I will teach you how to do that. So this is the things that you need to consider, or when you're designing an embedded system, how to deal with this ADC and keep noise-free ADC signal. Otherwise, you will find your readings are not accurate, right? So your program is running perfect, but you won't get any value. So you are desperate. What is happening? It is happening because of the bad layout, or you are not following this manufacturer's specifications. So it is all about hardware and software when you're dealing with the embedded system, right? A bad layout will ruin your system. Right, so this is the basic concept behind the analog to digital converter. And first, this is what is the signal coming from any ADC channel, right? Any ADC pin. Let's say ADC pin number 1. So that's the ADC analog signal comes here with respect to the time. So it has an analog buffer, right? Analog buffer is just an op-amp. Think about it's an op-amp. So the non-inverting input is connected to your signal, and the inverting signal is connected to the output. So the thing is, like whatever the gain of this one is 1. Whatever the signal comes here will be appeared here without any modification. The thing is, the using the analog buffer is to avoid any loading. I mean, sometimes, you know, the op-amp has a high input impedance, right? Whatever the signals comes here goes to like maybe 1 mega ohm resistance should go, right? So it has a high impedance for whatever the voltage source that you are connecting, which generate this analog signal, right? So there's a high impedance, which means you are not loading your source, right? If this resistance is like 100 ohm or something, most of the voltage will drop across this internal impedance or the output impedance of the source, and you will get like a very low value here, right? Let's say like this guy generate 5 volt here. This is 100 ohm, right? So if this is 1 mega ohm, the voltage is approximately 5 volt, right? Because due to this high impedance, most of the voltage is drop across this 1 mega ohm resistor, and very low value will be dropped across this 100 ohm. But when it comes, this guy has a like a other than like a 100 ohm resistor of input impedance, then you will know like only 2.5 volt will be available to you. Other half will be dropped across your impedance of your source, right? So it's a very bad. So always you need to have a high impedance. So the op-amp will do that for you. That's why you're using analog buffer to keep stop loading your circuit and get the whatever the voltage coming from the source appearing here. And you need to have a sampling and hold circuit, which means like so you sample your circuit, the signal. So let's say like this signal will charge this FET. When this FET is on, it's acting as a short circuit, and keep this capacitor charged to the whatever the voltage here, right, to this level. So the capacitor is charged here. So then you disconnect this FET, and you can keep the charge capacitor voltage. It will be something like that until you process your ADC operation, right? That's why you need sampling and hold circuit. The capacitor is charged to this voltage, and it will keep the charge until you perform your ADC operation. Here also there's a analog buffer, because if you don't have any high impedance, this capacitor can just quickly discharge, right? So this is 1 mega ohm range in input impedance, so that will keep the capacitor without discharging very fast. And then there's an approximation circuit, which is called successive approximation ADC, which is used in Atmel microcontrollers, and then you convert whatever the analog value to digital value. And this is this sample and hold how it looks like. This is your input signal, and this is that FET switch. So when it is driven from like a clock source, digital pulse. So once this is on and this is closed, once this is 0, this is open. Once this is on, the capacitor charges, and it will hold that whatever the value here. For example, now if this switch is turned on here during this period, and the switch is on, the capacitor charges here. And once the switch is open, so the capacitor charge will be kept during this period. So whatever the signal is appearing here, something looks it looks like this, not like a continuous signal. It's like a, due to this capacitor effect, it is something like that. So this is how it is happening, right? So this is your continuous signal, and then this is this pulse. And this is the sample signal. Here you can see during this period when the switch is on, the continuous signal is appearing here, right? So it will keep this capacitor to charge whatever the voltage here. So the same voltage will be here. And here again, that voltage. This is the sampled voltage. So what is appearing here will be like the capacitor is holding that charge. Whatever the voltage here will be continued until the ADC is done. And when you turn on it again, this this voltage of the signal will be repeating here. And when you stop it, this voltage, end voltage will be continued until the next period. Again, when you turn it on, this voltage will appear in here. Likewise, this continuous signal is distorted, but it will be something like that happening here, right? If you want to have a smooth waveform appearing here, you need to have fast switching and fast sampling frequency. All right. So you need to know several terms and references of this ADC. The first one is sampling frequency and the reference voltage, resolution, and quantization. So let's take a look at what is the sampling frequency. So the sampling frequency is the speed of the conversion, which means like you can take the samples here, 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 and here. So the sampling frequency is just this time period, 1 upon this time period. This is the sampling period. So it is these gaps are very equal, right? So when you're having high sampling rate, so you can have the original waveform without having a distortion. When you have low sampling rate, it would be more distorted and discrete, right? So the number of samples taken per second is referred as the sampling frequency. Sampling is taking snapshots values of the analog signal to have an accurate representation of how the analog signal is changing over the time. So it sampled here and keep this voltage continued until the next sampling point. So the ADC sampling frequency must be at least twice the analog signal frequency. So this sampling frequency should be twice than this original frequency. If this is a sine wave with the let's say like a 100 hertz signal, so you need to have like a sampling rate of at least 200 hertz in order to get this ADC done. This is known as Nyquist theorem. This is again an example like 10 microsecond ADC can sample the signal of 20 microsecond, right? Which is equal to 50K. So you need to have 100 hertz sampling frequency. If you want to sample the 50 kilohertz, 100 kilohertz sampling rate to sample the 50 kilohertz signal. Otherwise, it will be distorted and you can't get any accurate reading from the ADC. And the reference voltage, I have shown you in the microcontroller, there's a reference voltage pin. So definitely you need to have a reference voltage when you're doing the ADC. So the ADC digital output value is the ratio of the analog input with respect to the reference voltage. Okay. So either you can select the AVCC voltage or the internal reference source, bandgap reference, or any external voltage source connected to the ARF pin. Now this is a example. So the digital value can be calculated using analog input voltage divided by analog reference into 2 to the power n minus 1. Here the n is the ADC resolution. I will explain what is resolution. For example, now if you take 12-bit ADC, so it will generate like a 12-bit digital value. So if your input signal is 1 volt, this is the analog voltage signal, is 1 volt, and your reference voltage is 3.3. What is the digital value? So what is the output of the ADC? So it is calculated from this one. So analog voltage is the signal, original signal voltage is 1 volt, divided by reference voltage is 3.3 into 2 to the power n minus 1. 2 to the power 12 minus 1 is equal to 4095. So it will produce 1240 in decimal or 4DH in hexadecimal. So this is the decimal value, and this is the hexadecimal representation of the digital value. So it's a very simple calculation. The thing is, you cannot go over than the reference voltage, right? Let's say like you have this 12-bit, so your analog signal should vary from 0 to maximum of 3.3 volt, right? It cannot go beyond the 3.3. Now, let's say 12-bit ADC, right? So the maximum value is 2 to the power 12 minus 1. This is the maximum value that you can represent for 3.3. And the lowest value is 0. So this, whatever the 3.3 will be split into this kind of small segments. The maximum value is this one and the lowest value is this one. Okay. So if you're having any voltage between 3.3 to 0, for example, now 1 volt, you will have a value from the value represented for that. It's like a proportional, right? So this is the equation that you need to remember when you do these calculations. Right. So the ADC resolution is another term, which is defined as the smallest increment of the voltage, which is causes the change in the digital output. Now, so in the AVR microcontrollers, you're having 10-bit ADC resolution, which means the maximum value you can have is 1023. If it is 12 bits, 4095, and likewise, right? So PLCs has this kind of resolutions up to 16-bit. Some microcontrollers also having 12-bit. You can use a 10-bit to have a 8-bit resolution in microcontroller, right? It's always you can go below lower value if you're having higher storage. Right. So the lowest value is you have to just divide the whatever the voltage. For example, 3.3. When you divide it by this number, will give you the lowest value that you can measure, which is a resolution. Right. So you can see here, like this is a low resolution and low sampling rate signal. This is your original signal, analog signal. So when you sample it at a low frequency, this is the digital representation, right? So it is very much distorted. When you're having a high sampling rate and high resolution, you can like here you can see it sampled here and sampled here, right? So but the voltage level changes something like that, right? Very wide range. But when you're having a very low resolution, like a 10-bit and 12-bit, like a very high resolution, so you can change small segments, right? So you can like your digital value is just following your original analog signal. When you're having low sampling rate and low resolution, the signal is distorted. Yeah, this is the what I already discussed. The smallest increment is the smallest voltage that you can measure, which is given as the least significant bit. So that is equals to the ARF voltage divided minus the this analog ground voltage, which is normally 0 volt, divided by 2 to the power n. For example, now with the 5 volt reference, analog ground is 0, a 10-bit ADC resolution, the smallest increment is 5 divided by 1024, which is around to 4.8 millivolt. Right? This means that the change of 4.8 millivolt analog input, the ADC converter digital value will be changed by 1 LSD. In reality, there are 2 to the power n minus 1 steps. So this equation should be corrected to this one if you need a more accurate value. But for the approximation, you can use this equation, right? So which is the smallest increment is something this value. So that is ARF minus 0 divided by your resolution minus 1. Quantization is another term related to the ADC. Quantization array is introduced by process of quantization. Now let's say like this is a 3-bit ADC encoder. 3-bit is like a maximum value is 111 and the minimum value is 000. 111 is 7, right? And this is 0. So you can see here like 0, 1, 2, 3 up to 7. And you can see here from any voltage level, right? From 0 to this is 1/8, half of that, right? You can either have this voltage level because this is a binary representation, right? This is 0, this is 1, 2, 3, like that, right? So if it is the original reference voltage is, if it is 0, you can have 0, and you can go up to half of that one, right? During this region, it can only put your value, the digital value to here, right? So if it is over than that, I mean half of that value, 1/16, this should be 1/16. Any voltage level over than that, you will just push it to this value because the digital values does not have half values, right? So either it could be here, either it could be here. So any like it's like an approximation. Half of that, below that, you will push to here. Any value over than that, you push to here. And when it is 1/8, so accurately you will get this representation, right? These are approximated to this side and these are approximated to this side. So you can see the error like from here to here, the original value is increasing and you will still put into the 0. So the error is like when this original voltage increases, the error is increasing in this way. And when it comes for here, the original value is lower, but you represent it as 1, right? And it is going like that. And when it comes to 1/8, you will get 1 here, right? So it is there's no error. Here also no error. Here also no error. But any value between that, you will have a quantization error. So if you need to have more, if you can reduce the quantization error, you need to have more bits, more ADC resolution. So these are the basic definition of ADC, so which you need to know about. And the ADC converter inside your microcontroller need to have a clock source in order to work it. So the clock source, and it could be half of your CPU clock speed. There are 3 scales, 2, 4, 8, 16, and like that, right? Up to 128. So you have to select the clock speed by changing the values in this these bits, ADPSO, in this ADC SRA register. That's how you select the clock speed. Sometimes you don't need to have like a fast clock speed to run the ADC, because for slowly varying frequencies, you can have a slow speed, so it will reduce this processing time and save some power, right? So for example, now normally in order to get any reading, like in order to sample an analog signal, it takes 13 clock cycles. clock cycle means like a CPU is running with the let's say like a 8 megahertz oscillator. This is your CPU speed, and so either your ADC could run half of that, like 4 megahertz if you select the right value, or either 1 megahertz, and likewise. In this example, 8 megahertz system clock, you can have 4 megahertz because that is the either it could the lowest value is clock divided by 2, so it should be 4 megahertz. And it takes 13 clock cycles to perform an ADC because it cannot perform the ADC within a one pulse, right? Within a one clock cycle, it cannot complete all this ADC processing. So it takes at least 13 clock cycles. So 4 megahertz divided by 13 is this value. So it can do this number of conversions per second. So it means like a one conversion takes at least 3.25 microseconds. So this is the signal that you can. This is nearly 307 kilohertz sampling frequency, right? Sampling frequency is not the clock frequency. This is your sampling frequency, 307 kilohertz. So you can measure any frequency up to 150 kilohertz according to the Nyquist criteria. Any frequency over than that cannot be measured due to the hardware limitation of the ADC. Right, so you have to make sure you are doing the right, selecting the right clock speed based on your requirements. So from this point, I'm taking some examples using Atmega 328P microcontroller. So it has a 10-bit resolution. So whatever the value, analog value can be represented as a 10-bit digital number. 0.5 LSB integral nonlinearity, plus or minus 2 LSB absolute accurate, blah, blah, blah. So it has internal 1.5 ADC reference, and it has noise canceller, and it can have a maximum resolution of 15 kilosamples per second. Yeah. So right. So in Atmega 328P ADC, the ADC is connected to the 8-channel analog multiplexer. So you can have 8 channels, 8 pins, but in reality, through 328P has 5 analog pins only, right? So you can see that any analog pin using this ADC multiplexer, which are assigned to port A. So all the conversions are done with respect to the ground. Ground is your lowest voltage. It has a sample and hold circuit which ensure that the input voltage to ADC is held at a constant during the conversion time. Like I mentioned, 13 clock cycles are required in order to perform the ADC. So during that period, that the capacitor in the sample and hold circuit should hold the voltage, otherwise the values will not be accurate. Internet has a 1.1 volt reference. Sometimes you can use AVCC pin or external supply as your reference. When you're using AVCC, you have to couple at the capacitor to ARF pin in order to eliminate any noise. So normally you can the ADC in the microcontroller consumes power. When you are not using the ADC, you have to disable this ADC feature by writing logic 0 to you have to enable the ADC, or then you can disable this PRADC, power ADC, by writing logic 0, then only you can enable ADC, right? Most of the time the ADC is disabled, right? So you don't need to worry about. So if you use the ADC, then you can, when you're not using, you can just disable it, writing logic 1 to this bit. So it uses 10-bit digital value using successive approximation. So if you want to look at what is successive approximation, you can just go to the internet and search YouTube videos related to this one. So the minimum value represent is ground, and the maximum value is the voltage at ARF pins -1 LSB. So that's what I have already told. So these are the basic theory behind analog to digital conversion. Then we can move to the registers of the ATmega328P to use the ADC for programming purposes. All right, so these are the registers that you need to deal with when you're writing the codes. The first one is ADMUX, in order to select which pin or which ADC channel that you want to get the ADC done. And the second one is ADC SRA, the ADC control and status register A. And there's another one called register B. And whenever you have completed the ADC conversion, so the digital representation is available on these two bytes. Okay, so we have to read these registers in order to take this digital value of the analog representation. Right, so this is the ADMUX multiplexer selection register. So like I mentioned, so this bit 7 and 6 is to select the ADC reference. So you can, when it is 0, it is for internal reference is off, and you are getting the whatever voltage connected to the ARF pin. And if you write this bits as 0 and 1, so you are selecting the AVCC, or supply voltage to the analog port of your microcontroller, but you have to connect a capacitor to ARF pin. And this is reserved. And if you want to select the internal band gap reference 1.1 volts, so you have to write 1 and 1 to these two bits. And so ADLR is your digital value. Either it could be left adjusted or right adjusted. I will explain it later. And from here, you can select this ADC channel, right? So if you want to select ADC 0, so you have to write 0. If you want to select ADC 1, you have to write 0, 0, 0, 1. You can go up to 5, right? So these 5 pins are available in the microcontroller. And this is not available in a ATmega328P. And this is, you can also measure the internal, there's an internal temperature sensor. If you want to read that, you can write the ADC 8. So that temperature is very much representation of your CPU temperature. So if this is over temperature event, you can shut down your microcontroller to protect it. So the thermal measurements can be done using this temperature sensor. So it is not access to the outside world, but internally when you read this one, so you will get the temperature representation of the internal temperature sensor. And sometimes you can sample the ARF or sample the ground. Sometimes the ground might not have at the 0 voltage level, so you can, any offset can be measured. Or sometimes the band gap reference might not be accurate as 1.1 volts, so there could be offset. So you can try and remove these offsets by reading these values, and that is out of this lecture. So basically, you need to understand, like whenever you want to do a ADC, you have to select the right ADC channel by writing to these registers, and the analog reference voltage should be selected from these pins, and the your data, the way that you represent your data is depending on here. So by default, it is 0, it's left adjusted. Writing 1 is left adjusted. Other by default, it is right adjusted. Okay. This is a ADSRA register. So there are some bits. So first is you have to enable the ADC by writing digital 1 here. Otherwise, you can't do any ADC conversion. So you have to enable all this analog digital converter by writing 1. And if you want to start the conversion, you have to write 1 to this bit. And sometimes you can have like a to run this ADC, your ADC block. You can send like you can write 1 here and start the conversion, that one method. Sometimes you can start the conversion by external source, right? External auto trigger, some like a clock from my interrupt or something like that. So that is sometimes useful. And once the ADC conversion is done, it will generate a interrupt flag. So this is the interrupt flag. So once the conversion is done, this bit become high. And if you want to have this interrupt flag, you have to enable this by writing 1. So the interrupt should be enabled by writing here. Then you can have the checking by interrupt flag. You can whether know you can either know the conversion is done or not. And this final thing is for clock selection. Like I mentioned, you can select the clock when it is 0. The division factor is 2. The CPU clock frequency is divided by 2. It is 1. Again, it is divided by 2. If it is 1, 0, the CPU clock speed is divided by 4. Likewise, you can reduce the clock speed of the ADC. All right, so the ADC, this is how you save your 10-bit data. So once the ADLR register, this one, when it is 0, so the topmost bits are saved in ADCH register, and the bottom ones are saved in the bottom register, right? And when it is right registered, so all the bits are shifted here. The most significant bits are shifted here, and the least significant 2 bits are shifted to here. If you want to read 8-bit ADC from the 10-bit, so you can set ADLR and just read these 8 values. This register will be enough to have 8-bit accuracy. Otherwise, if you want to have 10-bit, you can read these 2 bits and read these 2 bits and do some calculation, right? So this can be multiplied by 256 and plus this value will give you like a 10-bit representation of your ADC. Right. So ADCSRB is to select that auto triggers mode. If you by default is free running mode, right? So when you select this bit ATE, so you are free running. So every time the ADC do a conversion and complete and start the next conversion, like that is repeating. And you can start the conversion with the interrupt of the analog comparator. So the analog comparator output is when it is high, you can start the ADC conversion. Or you can, with the external interrupt request, you can start the conversion. Likewise, the ADC start can be triggered by using any trigger source by writing to these 3 bits. Right. So like I mentioned, this is this Atmega 328P operation. So by writing to the ADC MUX register, here, the channel can be selected. This is that channel, right? So you write to ADC MUX register, so it has a decoder. So whatever the value you written, it will select the particular channel. Sometimes you can select the temperature sensor and get the temperature reading, or sometimes you can measure the band gap reference voltage, or sometimes you can measure the ground voltage. And this is how you select this analog reference, either it is internal or AVCCO reference. So basically, this is all about it. So if you want to enable the ADC, you have to just write the set the ADEN in ADS array, like I mentioned. This bit should be set. So everything I have explained here is repeating in this slide. And there are 3 modes of operation of ADC. The first one is single conversion on demand, which means like you request the ADC to complete it and it will be done the job. The second one is free running continuously, which means every time once the conversion is done, it will start the next conversion and it will start the next and so on. And clock conversion is periodically. So you by defining this interrupt, this auto trigger mode, you can start any conversion based on whatever the either from a change in the analog comparator or any external interrupt or timer counter. These things I haven't taught you yet, right? From any external source, you can give a command to the ADC to start the conversion, right? In single conversion mode, is started by disabling the power reduction bit and starting ADEN, and writing the logic 1 to AD start conversion bit, right? So if you write this, if you set this bit, so it will start the conversion. You have to set this bit enable and then start conversion bit set, then the conversion will be done. So this bit, once you set it, it will stay high as long as the conversion is in progress and will be cleared by hardware once the conversion is done. So this is how you know either the conversion is still running or not, right? So you have to select the channels and all these clock sources before you set this conversion bit. So if you select a different channel while the conversion is going, the ADC will finish the current conversion before performing the channel change. The free running conversion, like I mentioned, so once any conversion is done, it will repeatedly start in the next one. So free running mode is also comes in with the clock conversion, which means like you have to set this auto trigger if you want to set the free running. So first you need to set this ADATE for auto trigger, and so set clear these 3 bits. By default it is clearing, so you are in the auto running mode. So normally this is 0, which means auto running is disabled. So whenever you set this ADSC, you start the conversion and wait until it is done. So then you get the reading. And if you want to have free running, so you set this one, and all these other 3 bits here will be by default 0, so it is free running. Or either clock conversion, you can select any clock source based on the requirement and based on the request. So it will do the ADC conversion. Right, so to provide gives you freedom to start a conversion with fixed intervals. likewise, right? So I'm going to give you some examples. So here there's a resistor divider or the potentiometer. So the potentiometer is connected to the positive supply, and the other side is ground. So by changing this one, you can change the voltage from 0 to VCC. So whatever the ADC reading you get from this conversion should be displayed on port B. It is asked to use the AVCC as your reference voltage supply to the ADC converter as your reference, and the reading should be left adjusted. So you are just reading the 8 Morse bit. So it's 8-bit accuracy, and set the clock frequency to division factor of 2. Okay, this is your structure diagram for this code. So first you need to do the setup. So in the setup, so you select this channel 0. So select the channel, required channel 0, and reference to AVCC, and set port P as output to display your digital reading, and then turn on the ADC. So that is your setup, and then you are running on a while loop. So you start the conversion and wait until the conversion is done, and then get the results and display on port P. So this is the code for that. So you have to have this libraries, input output of AVR. And since we are using an internal 8 megahertz oscillator, so the available by using the fuse bits, so the available frequency for you for the CPU is 1 megahertz. So I have defined this registers start conversion. So in the ADS-C array, and ADSC like start conversion should be set, and you can check whether this bit is cleared or not by checking with this command. Either the conversion is in progress. So if you are not familiar with these things, just go and look at the digital output lecture notes previously explained, right? And I have defined port P as display, ADC value as ADCH. And this is my setup function. So first, if I want to display the value read from the ADCC to on port P, so I have to set the port P as output. So DDRB is 0 into FF, which means like 255. So all the pins are set as output. So initially I turn off the port P, so the output will be 0. You can either disable this digital buffer on ADC 0 by writing this DDI R0 to 1, but it is not essential. If you want to save the power, you can just use this command, otherwise you can skip it. Now you need to select your reference voltage source and whether the reading is right adjusted or left adjusted, and required channel. By default, this channel ADC node is there, right? Which means like ADC mux, if you go back here, ADC mux, so ADC channel 0 is 0, 0, 0, 0. So by default, all are 0. So you don't need to do anything on this 4 bits, right? So just leave it there. So it will select in the ADC node. But you have to select this AVCC. So then you have to write RF SO as 1, right? So AVCC should be selected as it is asked to use AVCC as your reference voltage. If you want to select the reference voltage, you can see AVCC as the reference. So SF1 should be 0 and SF0 should be 1, right? In AD mux register, SF0 should be 1, SF1 should be 0. Then you are using the AVCC pin as your reference voltage. Right, and your data should be right adjusted. In there, like I mentioned, right adjusted means you are reading the topmost bits of the 10 bits, right? These values. The bottom bits are neglected, so you are getting 8-bit accuracy of your reading, right? You are not reading all these 10 bits. You don't need 10-bit accuracy. In the problem, it is asked to get the topmost bits for 8-bit resolution. Okay. So it is now ADLR is set to 1, which is write register. Finally, you have to set the ADE enable the ADC by writing ADE in as 1, right? In the ADSR register. So all this set, and you have enabled the ADC. Now you are running to the main function. So calling the setup and done the job, and go for the while loop, and calling the start conversion. Start conversion is setting this start conversion bit. So once the start conversion is done, so you can wait. The conversion is in progress. It is checking this bit is whether it's 1 or 0. Like I mentioned, once you set, it will be set until the conversion is done and cleared this bit by the hardware once the conversion is completed. So you can continuously checking this one is 1 or 0. So you set it and checking whether it is cleared. So you are waiting in a while loop. While this is true, you are waiting here. You are looping. And once the conversion is done, you exit from this while loop. So you come to here, display. Display is equal to port P, and port P is equals to ADC value. ADC value is you are just reading the ADCH that register, this one. You are reading this ADCH because it is write register. So you are reading displaying these bits on your port P, right? So you have port B, port B. So this goes to the RB node, and this goes to the RB7. Likewise, for any analog reading, so you are displaying this bits on the port B. So there's a second example, and it is asked to change this previous example to free running mode. So the on the changes is in the free running mode. So you have to deal with the ADSR array. So you have to enable the auto trigger, right? And ADC SRB auto trigger source, by default it is free running mode, like I mentioned. So you enable the ADC, and ADC start conversion is set, and auto trigger mode. So this is the auto trigger mode. You have to set it, and set the start conversion, and auto trigger source can be selected from ADC SRB. By default, these bits are set to 0, so it is on free running mode, right? So you don't need to write anything on ADSRB. That's why I have left this as commented. So you don't need to write anything here. By default, it's on free running mode. So it is continuously sample and copy that value to your ADCH register, and you can just copy that value to your port B. Right? That is example number 2. And example number 3, it is asked to modify the code 1 to read this ADCL and ADCH, all the registered, to have 10-bit resolution while left adjusted for the channel ADC2. Now I'm using ADC2 channel, not ADC0. Display the results using port B for ADCL, because since it is 10-bit, you can either use port B as to represent this 8 bits, and the other 2 bits can be represented from port D. And also you can copy that ADC value to integer, right? So this is that code. Everything will seem similar. So now I'm using port B and port D to display the value. So I have to set the data duration as output. So it is on the single conversion mode, not free running. So you have starting the conversion and wait until the conversion is starting. Then you read the ADC results. So first you read the ADCL register, and then you read the ADCH and multiply it by 256. Then you can get the results copied to a integer, right? So this is the integer representation of your ADC. And port B is copied by this lower 8 bits, and the port D is copied by the higher 2 bits here, right? So because I have multiplied by 256, because you know, so it is like this, right? Left adjuster. So this here to here it is 255, and here to here it is 10 to the power, like this one is 10 to the power 0, and this one is 10 to the power 7, and 10 to the power 8, 10 to 2 to the power 9, likewise, right? So here to here the maximum value is 255, and these two values, when you get their binary, and you have to multiply it by 256 in order to add to this value, right? Because it is another bit on another bit. Or either you can read this value and multiply it by 2 to the power 8 plus this bit multiplied by 2 to the power 9. Or you can get this register and multiply it by 256, will give you the same result. Right, that's all about here. So without knowing ADC, I think that it will be difficult for you to move forward because any design technician, so you have to deal with the ADC conversion. So be careful. So you read all these lecture notes and listen to the recording again if you have any clarifications. If you have anything to know from you, you can ask now, or you can email me. So I will be available for you to answer your questions. So that will be end for this session. So thank you for listening.